Let's look at another problem that involves this next problem. We have a very similar situation, but here we have 30 grams of a toxic substance entering a 10,000 gallon pond each minute through waste runoff from a chemical company. Now that just means that we have sort of a larger drum here. This is the same kind of concept, but now our tank, our drum, is actually a lake. So when we talk about tank problems, it doesn't actually have to be a physical container. It could be something like a lake or a river, or the human body can be thought about as a tank. So to keep the water level constant in the pond, water leaves the pond through a stream at 20 gallons per minute. The pond initially has clean water. When will the amount of the substance reach a dangerous concentration threshold of 5 grams per gallon? So we're going to model it as before. We're going to think about what it is that we want to ask. Now, we never model concentration. Concentration is just the amount divided by the volume. So as long as we know the volume, we can figure out the concentration later on. We always want to define our variables as amounts. It's just too tricky to try to get into concentrations. So let Y be the amount of toxic substance, in pond. Well, that's measured in grams. And T is I'm just going to say time here, but we know this is the time since the substance begins polluting this pond. This is measured in minutes. And so one thing we should point out is that dy dt will have units of grams per minute. Now the one nice thing here is I'm already told how many grams are entering per minute. So when I draw my bathtub analogy set up here, what's coming in is strictly given to me as 30 grams per 1 minute. Now that's already in the correct units of the inflow rate. And remember, we're looking at inflow of substance minus the outflow of the substance. So here they don't tell me what the concentration is, so I don't have to multiply the units together like I did before. But one interesting thing is that if we know that 50 gallons or 20 gallons per minute are leaving in order to keep the water level constant, that must mean that there's 20 gallons per minute coming in as well. Now again, this is not something that you need to know for moving forward with this problem, but this 30 grams per minute has essentially already been figured out for us. So I have to ask myself here, what if I wanted to know at what concentration the salt or the substance is coming into the pond? I could just take 30 divided by 20, which is actually 1.5. So if I really wanted to know all those details for some reason, I could say, well, this would have to be 1.5 grams per 1 gallon in order for these two to multiply and give me 30 grams per minute. So again, just sometimes you get information that's you don't need to put together, it's already put together for you. And what's coming out? So once again, the concentration inside is going to be, there's going to be Y grams dissolved in 10,000 gallons. And so again, we have grams over gallons, and that's going to get multiplied by gallons per minute, which is 20 gallons per minute. And our dimensional analysis will tell us that we are in grams per minute. So this will come out to 20y over 10,000. And again, that's now in grams per minute. I'm also going to go ahead and reduce this fraction a little bit just to make it simpler. So this is 2 thousandths, and which is 1/500th. So I can write this as 1/500th y. That would just make it a little bit easier to work with. And so now our dy dt model is going to be the difference between our inflow and our outflow. Our inflow is 1.5 grams per minute. 30 grams per minute. 30 grams per minute minus 1/500th y grams per minute coming out. There is my model, my initial value problem. So now coupled with my initial condition, I could have said over here in this box, this is 10,000 gallons with no substance initially present. And so there is my IVP, my initial value problem, and I can now begin doing my calculus on this. So once again, this is a separable differential equation. I know that because there's no t in the equation for 1, and if I factor this out into 1 times 30 minus 1/500th y, and 1/500th is actually 1/5 would be 0.2, so this would be 0.002. That's an exact number, so I can leave this as 0.002. It'll make it a little bit easier to write down. So I'm going to divide over by the h of y, which is 1 over 30 minus 0.002y times dy dt equals 1. And now when I integrate both sides with respect to t, these will cancel, and now I will go ahead and integrate that with Wolfram alpha. And there you can see the result. So this will integrate to be negative 500 ln of 30 minus 0.002y equals t plus c. And now I can divide by negative 500. So that will leave me with natural log of 30 minus 0.002y equals, so this will be negative 1/500th t, or negative 0.002t. And then when I divide c by negative 500, that's an arbitrary constant divided by a constant, so I can just leave that as plus c. Now I'll exponentiate and make this ke to the negative 0.002t, subtract 30 and divide by negative 0.002, which leaves me with ke to the negative 0.002t. Remember, because when we divide k by a constant, it remains an arbitrary constant. And so when we subtract 30 and divide it by negative 0.002, we get plus 15,000 over here. And now we can solve for our initial condition. I'm just going to make the claim here that when you plug in 0 for y and 0 for t, you're going to get k equals negative 15,000. And so our final equation will be negative 15,000 e to the negative 0.002t plus 15,000. And you can go ahead and verify just to be sure in your own mind what that's going to be negative 15,000. Let's go ahead and graph this. Now remember, this gives me the amount. This is the amount as a function of minutes or time. And so if I want to know the concentration, remember I'm going to have to divide this by the amount of volume in that pond. Because I want to know not when does the amount of this toxic substance reach 5 grams, but when is the concentration of the substance 5 grams per gallon. So let's go ahead and analyze that. And so we'll just go ahead and plop this in to our graph. So we have negative 15,000 e to the negative 0.002x plus 15,000. Now I want to give this a function name. I'll just call this s of x again for substance. And now I probably should adjust my axes here. So this is time in minutes amount of substance. And not in the drum, but in the pond. And that's measured in grams. Okay, so I see first of all, I can verify visually, and we should have done this in the last graph as well, but at time 0, there's nothing in the pond. And as we begin to zoom out, we're going to get an ugly looking window, but that sort of flattens off all of a sudden. So I can tweak that a little bit. I see I probably don't want to go beyond time about 3,000 or so. So I'll just go ahead and take my x-axis from 0 to 3,000. And there we go. So that's a pretty good graph of the image. Now again, this is the amount that's inside of there. So clearly we reach 5 grams total very, very rapidly. That happens almost instantly just based on what's coming in each day. So if I want the concentration, which is going to be s of x divided by 15,000, not 15,000, 10,000, that's the amount of water inside that tank. I take S of X and divide it by 10,000. Now that's going to be very, very flat. That's just because the number of grams ends up being very large. But let me go ahead and zoom back into the standard zoom, and you can see the concentration is actually really low. So let me change my y-axis from something like 0 to, I'll start off with 0.1, and that looks a little too flat. Let me go 0.01. All right, well now we're getting somewhere. And I can start to slowly zoom out and see what that's going to look like. And I can see that that's starting to flatten out nicely over time. And now I can get in here and kind of tweak this a little bit. I don't want to go quite up to 4. I can see that that's going to be well below 2. So now I can change my x-axis to go to, let's say, there's 1,000, there's 10,000, probably up to about 5,000 minutes. There we go. That looks pretty good. And I can see that that concentration is approaching 1.5 grams per gallon. And that's pretty interesting because guess what? What we calculated back here was that in order for 30 grams to be entering per minute, without the volume changing, knowing that 20 gallons per minute are coming out, we were able to solve for the concentration coming in as 1.5 grams per gallon. So that's kind of funny, right? Because this is asking for when will the amount of the substance reach a dangerous concentration threshold of 5 grams per gallon? Well, we could have answered that question just by looking at the model itself. And so part of the purpose of this problem is we went through a pretty sophisticated analysis, but we could have answered that question had we thought about it a little bit more at the beginning, saying, well, the concentration coming in is only 1.5 grams per gallon. Therefore, this threshold will never occur. Even though that toxic substance is entering, it will never be at a dangerous level. But we answered the question, we just did a lot of work to do it. So sometimes when you think about problems a little bit ahead of time, you save yourself a lot of energy. So units can reveal just as much sometimes as an actual calculus solution method.